Start the video. Oh, good. Lots of people on. And okay. All right, let's start the screen share. Let's hope. Oh no, come on. Jesus. Oh, man, come on. Jesus. Thank you, man. Jesus. Sorry about this. It's infuriating. See if that works. Okay. All right. Let's hope. Well, didn't went off again. It went on again. Okay. Later. All right. Okay, let's get the screen going here. Okay. Okay. All right. Good. So we're almost there. Okay, let's see here. Oh, that's much better. And today is the 28th, is that correct? Okay, let's see, let's get the volume up. Okay, let's do a sound check from the other end. Someone on Zoom, if they want to speak up, please.
Hello, hello, hello.
Yeah, we can hear you.
Okay, we can hear you, great. Can you hear me?
Yes.
Great. Okay, so I think we're set. All right, so we did this in record time now. We're getting better at this. All right. Okay, let's see. First thing. So the first thing is about the video. I understand that people had some troubles with Kaltura. Is that correct?
Yes, sir.
Okay. I don't know, I tried doing it too. It wasn't too great. I actually just shared the videos on Zoom. So if you could try obtaining the videos on Zoom, I'd appreciate it. I'm hoping that I shared the last 3 videos of the class. So let me
Where
know
would you
if
see that?
everything looks good. Okay. So the thing is, they're good for like 30 days. So so I'm hoping that that'll be enough time for you. And I've also I posted the notes on ELC from the class. So all the notes from the class I'll post on ELC. Okay, so you'll have hard copies of the notes available to you. Okay. All right. The next thing is about the grading. So you should have received a message from the grader that your folders in OneNote are set up. So did everyone receive a message? Yes. Yes? Okay, good. All right, so try that out. If you have any problems, just send me an email, or if you have I don't know if the grader actually gave her email or not. Did she give her email or not? No? Okay. Well, if you have to, just send me an email if you have problems uploading. Okay. I know that the first week is sort of a transitional week, and so we're not going to have like a super hard deadline or anything about the homework. So, I mean, we want you to turn it in sometime on Wednesday to shoot for that. Okay. All right. Great. All right. So let's hope this works today. Okay, good. All right, so let's start back in. And let me back up a little bit and review some of the ideas that we had from the last class, and then we'll go back to the problem that we sort of left off. All right. So last time we were talking about vectors in n-dimensional space. And the way that we describe the vectors in n-dimensional space was as column vectors. So things like x1, x2, x3, up to xn. So they have n coordinates, and each of the coordinates are real numbers. Okay? And so we label this vector like v like this. Now, whenever you have vectors, we have vector addition. So we have an operation called vector addition. So we can add vectors. And then what we could do is we can also scale vectors too. So we have this other operation where we can multiply, so it's called scalar multiplication. Right? All right, so last time we were interested in combining vector addition and scalar multiplication together, and that's how we form linear combinations. Okay, so when we have something of the form like C1 V1 plus C2 V2, let's call this W. So W is a linear combination of V1 and V2. All right, so let me recall the formal definition of linear combination. So here's the definition. So let V1, V2, all the way up to VT be vectors in Rn. Okay, they're T vectors in Rn. Okay, so Y is a linear combination of, okay, let's say, let me just put this at V1 up to Vt, if and only if Y is equal to C1 V1 plus C2 V2 plus CT Vt for some value C of j in R. J equals 1, 2, up to 2. Okay, so basically the idea is that when you have a vector, in order for it to be a linear combination of a set of vectors, you have to be able to find coefficients, like C1 up to CT, where you can sort of write this as like C1 V1 plus C2 V2 plus CT Vt. Okay, so pictorially, this looks like the following. So I can't draw T dimensions in general. So let me just draw 2 dimensions. So if I have V1 over here, and I have V2 over here, then any linear combination of V1 and V2 will have to lie in this plane. Okay. So this will be like C1 V1 plus C2 V2. Okay. So linear combinations. Sorry, let me make it a little bit neater here. Got a little bit too excited. Okay, linear combinations of V1 and V2 lie in this plane. Okay. So in higher dimensions, you can imagine, like if you have 3 vectors and they turn out not to be, each of them are not in the same plane as the other 2, then you can get something which looks like 3-dimensional space, et cetera, et cetera. Okay, any questions up until this point? All right, so let's go back. Now that we've sort of caught up here and reviewed, let's go back to the example and show that when you take the linear combinations or look at trying to express something as a linear combination of the other vectors, it's the same thing as looking at solving a system of equations. Okay, so let's go back to this example. So the question that we were looking at the other time was, is the vector 11 minus 5, 9 linear combination of the vectors 1, 0, 1 and minus 2, 3, minus 2. Okay. All right, so in order to answer this question, what we do is we just start by first writing down what it means to be a linear combination. So we're asking whether 11 minus 5, 9 is equal to a constant times this vector plus another constant times this vector. Okay, so this is what we want to know. Can we actually do this? All right. What does this mean? It means that we have 11 has to be equal to C1 plus minus 2C2 minus 5 has to be equal to, I'll just put 0 times C1 plus 3 times C2, and 9, so the 9 here, not a 1. So 9 is equal to C1 plus minus 2 times C2. All right, so if you just write out what these vector equations mean, you just get a system of equations. There are 3 equations and how many unknowns? How many? 2. Okay. So this is a 3x2 system of equations. Do we know how to solve this? Yes.
Yes.
So what method do we use?
Elimination.
Good. So we're going to use Gaussian elimination. Our favorite tool. Maybe our only tool. Okay. So now we just sort of put it in the form that we'd like. So let's do that. So this is 1 minus 2. We have 11 here. We have a 0, and we have a 3, and we have minus 5, and we have a 1, and a minus 2, and a 9 here. Okay? All right. Now we'll use Gaussian elimination. And so we have a pivot right there. We have a 0 already in the second row below the pivot. So we just have to eliminate the 1 in the third row. Okay? So I'm going to multiply the first row by minus 1. I'm going to add it to row 3. And I'm going to place it into row 3. Okay? So let's see what we get. We do that. Okay, so it's 1 minus 2, 11, 0, 3, minus 5. We get a 0 here. What else do we get? What's the next term? 0, good. And the next one is? Minus 11 plus 9 is? Minus 2. Okay, good. All right. So we're down to this stage. Does anyone want to say what happens now?
There are 2 zeros that equal -2, which can't happen.
Right. So the last equation says what? It says that 0 C2 is going to be equal to minus 2, right? And so there's no way, no C2, which is going to actually satisfy this. So there's no C2 that satisfies this. Okay, so this system, is it consistent or inconsistent? It's inconsistent. Therefore, is the answer yes or no? Okay, no. Okay, so no. So I don't know if I want to write the whole thing out. So let me just say it this way. Let me do some little shorthand here. Okay, so let's call this one Y, and let's call this one V1 and V2. So I don't have to write everything out. So Y is not a linear combination of V1 and V2. So Y is not a linear combination of V1 and V2. Okay, any questions on this, how we did this? So to determine whether something is a linear combination or not, we can just sort of set things up so that we can use Gaussian elimination. We'll definitely talk about this more later in a more general context. All right, now related to the notion of linear combination is the notion of span. Okay, so let's talk about the notion, what I'm going to call span. Okay. So the way to think about span, it's not span. Okay, span is the meat. Okay, span relates to vectors. Okay, so the idea is that you take a bunch of vectors and you want to see what linear combinations you can generate by using those vectors. And what you generate using linear combinations is called the span. Okay, so let me make a definition. So let V1, V2, again Vt, be vectors in Rn. Okay. So when I say the span of these vectors, what I mean is all possible linear combinations of them. So C1 V1 plus C2 V2 plus CT VT. So this is a typical linear combination, and where the CJs are real numbers for j equals 1, 2 up to t. And this is set notation. So that it's a set of all linear combinations. Okay, so let me just write that out. So it's a set of all linear combinations of V1, V2, V2. Okay. All right, so what I'm going to do next is I'm going to sort of write some examples out. So why don't we try that? Maybe I can use a little color this time too. All right, so let's do some examples of span. Okay, so the first example I'm going to do is just take one vector. So let's say I take span of a vector, let's call it V1. It's one vector. I don't know, let's say it just lies in two-dimensional space here. So the vector looks like this. Okay, it's V1, right? All right, so when I look at the span of V1, so I'm looking at all possible linear combinations of V1. What do you think we get?
A line?
A line. Very good. So what I'll do is I'll put in the nice, let's say, blue color here. Let's see if I can do this. Whoops. The blue color. All right. So the span here will actually be this line here. So L. Okay. So the span here is equal to the line L. Okay. Let's do two vectors here. Okay. Okay, so let's try a second example. 2. So let's say I have two vectors, V1 and V2. And let's say that they are on the same line. Okay, so here's V1 here. Okay, and let's say V2 goes in the opposite direction. All right. What is the span of V1 and V2 look like?
Is it nothing?
Well, I'm looking at all possible linear combinations of V1 and V2.
A line again?
it's a line again, right? Because the thing is, I get any linear combination of V1 is just a line, right? So it's like having C1 V1 plus 0 times V2. Any combination of V2 is also on the line, same line. So when I look at the totality of linear combinations, I still get the line. Okay, so let me just do that. And so I'm going to put this line over here. Let's call it L prime here. And so that's going to be the span. All right. Okay, now let's pretend, let's actually not pretend, but just say that we have two vectors, and let's say they're not on the same line. They go in two different directions, right? So it could be in three-dimensional space, for example. So what does a span of V1 and V2 look like?
A plane.
Plane, good. So the span here will look like a plane. Let's call the plane P here. Okay, any questions on this idea at all? All right, so now let's try to test our knowledge, and I'll give you a problem to do. Okay, so here's the problem. And we'll kind of just test our sort of knowledge about how to solve this problem. So here's the problem. So find a value h such that the vector 3 minus 5h is in the span of these two vectors. 1, 3, minus 1, comma, minus 5, minus 8, 2. Okay, so I want to find an h such that this thing is in the span of these two vectors. Okay, so let me ask you, what should we think about doing to solve this problem?
I think we should put some coefficients in front of, so C1 and C2 for the span, so we can get a plane, and we can use the matrices and Gaussian elimination to find out h.
Let me ask you a question. Okay, you have the right idea. What is the operative word? You want to know whether 3 minus 5h is a blank.
Linear combination.
Linear combination.
So we want to know whether, and this is just exactly what you're saying. We want to know whether 3 minus 5h is a linear combination of these two vectors, right? So the question, which is equivalently, so I'll just say equivalently. Yeah, I don't know if I spelled it right. So is 3 minus 5h a linear combination of these vectors? Okay, so that's what we want to know. Okay, and as you pointed out, we can set this up, and then we could just do exactly what we did in the last problem. Okay, so we want to know whether C1, times 1, 3 minus 1 plus C2 times 5 minus 8, 2, whether that's equal to, when it's equal to 3 minus 5H. Okay, so that's what we want to do. We want to see if there's C1 and C2, and we want to see when this is consistent. Okay. All right, so as you know, so now we apply the Gaussian elimination. I'm just following what you told me to do. Okay. And again, so now we just turn the crank, right? This is all we do. So a lot of this class is, we ask you questions, and then you sort of figure them out, put them into system equations, and then you just turn the crank. So here's 1, 5, 3, 3.
Shouldn't that 5 be a negative 5?
Sure, yes, you're absolutely right. So that should be negative. Let me just make sure the coefficients are right. Very good, and that's a negative right here. And make sure, did I catch everyone? Make sure I didn't drop any negative signs here. Okay, 3, thank you. 5 minus 2, 2, and an H here. Okay, everyone all right up until this point? All right, so let's do this. So, so here's a pivot again. I'm going to multiply by minus 3 times the first row, add it to the second row, and then put it in the second row. So let's just do that. So what do we get? We get a 0 here. What's next? 15 minus 8, that's what? 7, right? And then minus 3 times 3 minus 5. What's that going to be? Minus 9 times minus 5.
Negative 14.
Negative 14. Okay. Oh, that's interesting. All right, we'll just, that seems okay. All right, now what I'm going to do is I'm going to multiply the first row by 1. So I'm going to take row 1 and I'm going to add it to row 3 and then put the result in row 3. Okay. So I get 0 here. So I get 1 times minus 5 plus 2, that's a minus 3, right? And then I get 3 plus h, which is just 3 plus h. Okay, is everyone okay up to this point?
Yes.
Okay. All right. Now what I can do is I can sort of, so if I take any equation and I divide by something non-zero, it's going to be the same equation. So I'm going to divide now row 2 by 7. Okay, that's not going to change the system of equations. All right, so let's do that. 1 minus 5, 3, 0, 1, minus 2, 0, minus 3, 3 plus h. Okay, so I made the pivot 1 now, which is much easier to work with. Okay, so there's my next pivot. What multiplier should I put in for the second row? How about 3? Yeah. So I'm going to take 3 times row 2 plus row 3, and I'm going to put the answer into row 3. All right. Okay, so let's do that. 1 minus 5, 3, 0, 1, minus 2, 0, 0, and what do I get? I get h plus 3 minus 6, so that's what? H minus 3, right? All right. make sure I did this correctly here. Divide by 2 should be okay. Yeah, should be right. Okay, any questions on this so far? All right, so when is this system consistent?
When h equals 3.
All right, so the system is consistent if and only if h is equal to 3. Okay, so that means that the answer is yes if h is equal to 3. So the answer is yes if h is equal to 3. Okay, yes means that it's a linear combination of these things. Okay, any questions on this?
I have a quick question.
Sure.
So when you divided the row by when you divided row 2 by 7, couldn't you have just used back substitution there to find out C2 and then from there plug that into the third row for like the third equation?
Yeah, you could do it that way too. It's the same. It's exactly the same. But the thing is, when you have like lots and lots of equations, this way is better because it's a little bit more systematic. Because what you do is you sort of get it into the upper triangular form and then you back substitute back up. So. But you can do it that way if you want.
Would you write out the rule you used to get to the last matrices?
Oh, you mean okay. So I wanted to knock out this -3 here, right? So what I want to do is I want to multiply row 2 by 3, add it to row 3, and then replace row 3 by the resultant. Okay? So here I got 3 plus -3, I get 0. -6 plus h plus 3 is h minus 3. Okay? So that's how I get this one over here.
And the last matrix is in echelon form. Is that correct?
That's correct. And so that's why we can now try to back substitute up. And you have a consistent solution. You have to have zeros on the bottom row to have a consistent solution. So that means h minus 3 has to be 0. So that means h has to be 3. Okay? I think you have some homework problems just like this. Is that right? Yeah, okay, good. Hey, help someone out on some homework.
I do have a question about the homework with a similar problem.
Yes, so you can ask me. I actually am going to have office hours on Monday, so if you should work on that, and then if you have a question on it, you can either email me or we can set up office hours on Monday. If you are going to be in class on Monday beforehand, I can always meet you before class on Monday in order to talk about homework. Okay?
Okay.
Good. All right. So now we could actually move on to next week's topics. So I'm going to get a little bit of a head start. So let me just draw a line here. And so we're going to talk about the matrix equation. AX equals B. Okay, so the first thing is I'm going to set up what A times X means. So when I write A times X, I'm going to take a matrix here, and this is going to be M by M matrix. So it's A11, A12, A1N, AM1 up to AMN. So this is an M by N matrix. Okay, so basically it's an array with m rows and columns. And when I write x1, x2 up to x of n, okay, so I'm gonna tell you what I mean by what happens when I multiply these two matrices together. Maybe you've seen this before, but I'm just gonna formally make a definition, and then later on we're gonna talk about general matrix multiplication. All right, so here's the definition. All right, this is being equals. So what you do is you basically take x1 times the first row plus x2 times the second row and then you take xn, the last one, times the last row. Okay? Okay, so that's what the definition is. So it's basically saying the following: when I take A times X, I take the columns of the matrix A, and then I sort of write them as linear combinations using the X1s up to Xn.
Does the order of the matrices matter?
Order of the matrices. Order of the entries definitely matter. Okay? And we'll see that in a second. Okay, we'll do an example. All right, now let's just write this out. And you'll see, so what does this mean? Well, let me say, okay, we'll just do this. So if I write it as a big matrix here, this means A11 X1 plus A12 X2 plus A1n Xn. Okay, so this is a column again, and it's AM1 X1 AMN Xn. Okay, so this is actually a column with these entries in each of the column spots. All right, so let's do an example of this. Okay, so here is 1, 4, 3, 0, 1, 2, and I'm going to multiply times 6, 2, 1. Okay. All right, so let's write this out. So what is it? Well, we go back up to the definition. I want to take the columns and then sort of write them with weights 6, 2, and 1. So it's 6 times the first column. So what's the next term?
2 times the second column.
Thank you. And then 1 times the third column. Okay, that's all it is. And now let's just kind of combine everything. So this is going to be 6 plus 8 plus 3. And it'll be 0 plus 2 plus 2. Okay, so the answer is 17 and 4. Okay, any questions on this example?
Yeah, I got a question.
Yeah.
What does the 17,4 vector mean, like graphically? Like why did multiplying those give a 2 by 1 matrix?
So that's what the definition actually gives you. That's the point. Because, you know, you look up at the definition, right? The definition here actually gives you a column vector. Right, it just this sum is also it's just a linear combination of the columns, so you're just going to get another column. So when you write this out, you get a linear combination of the columns, and then you can just combine everything to get an actual column vector.
Okay.
Okay? And that's actually a good point because we're going to bring that up next.
I have a question as well.
Yeah.
What if there's like a mismatch of columns and rows?
You can't do it. You can't do it. It's not defined.
Okay.
It's a very good point too. Matrix, this multiplication is only defined if your dimensions coincide correctly. It's not always defined, so. Okay, now I'm going to start out sort of, and we're going to reverse engineer the process. Okay, so I'm going to start with a system of equations. And let's say it's m by n. All right, so what does a system of equations look like? We have m equations and m unknowns. So let me write that out. So that's a11 times x1 plus a12 times x2 plus a1n times xn is equal to something like b1. Okay, this is one equation, one linear equation. It's some sort of, n-dimensional plane. Okay? And then I write another one, a12 x1. Sorry, this is a21. Apologize. Let's use the eraser here. Okay. Go back. 2, 1. Okay. So a21 x1, a22 x2 plus a2n xn is equal to b2. Okay. And then let's write this out. So this is am1 x1, and the last one is amn xn is equal to abm. Okay, so they're m equations, right? So they're mb's. Okay, so we would hate to have to write this out every single time, right? So every time we had an n by n system of equations, it'd be a real pain to write all this out. So what we can do is we can kind of go back to what we did over here, and notice that when I write a times x, then I actually get the left-hand side, right? So the left-hand side is a times x. Everyone agree with that? It's just this right up here, right? And then I could just equate this to b, okay? Where b is the vector just given by b1, b2, up to bn. All right? So the upshot of all this is that ax equals b is a shorthand way of writing out a system of equations. It's a compact way of writing a system of equations. So this is a compact way of expressing a system of m equations and n unknowns. Okay. And the nice thing about this ax equals b is it sort of fits in well with our Gaussian elimination too, right? So when we have ax equals b, we can sort of write things out as a matrix in our Gaussian elimination on the left-hand side, and then sort of b as a column vector on your right-hand side, and then we just draw the arrow down to actually separate the a and the b out. Okay, so everything is smooth in some sense. We actually have a nice, efficient way to write out systems of equations. Okay. Are there any questions on this? transitioning from systems of equations to this kind of more compact way of doing things. Okay, great. So next time what we'll do is we will use this AX equals B formulation and look at spanning of the columns of A. So let me say what next time is. So next time, we're going to look at the connection between the solutions of AX equals B. And we've done this already, but we'll just do it a little bit more generally. And whether B is in the span of the columns of A. And you kind of know what the answer is. If we have a solution of AX equals B, that means exactly that B is in the span of the columns of this matrix. Okay, but we'll make it more precise next time. Okay, so let's stop here, and I wish everybody a happy and safe week.
Thank you, Professor.
Oh,
Thank
welcome.
you.
Thanks.
So the homework you said due like next Wednesday?
Yes, yeah, yes. And the grader gave you instructions on how to upload.
Yeah, I can do it.
Great. Okay,
Thank you.
okay, have a good weekend.
Thank you again.
All right, you're welcome.
What is that symbol between the letter B and the word span?
Oh, it's an element of, I'm sorry. So this is a, sorry, I should explain this a little bit better. Oops. So this word, this E means is a member of the set. So is B a member of the set, the spanning set? Okay, that's what we're saying. So another way is, it also means in. So is B in this set? Does that make sense?
Yes, it does. Thank you so much.
Good. Great, other questions? Thank you. Have a good weekend. Okay, you too. Okay, great.